Okay, this is lecture 12. So today's lecture is particularly important because today we will talk about a relation between our silicon charge and surface potential. So that is really particularly important. So please concentrate on today's lecture contents. Okay. So let me just dive into our main topic directly. So we are now talking about the surface potential. So surface potential is now defined as the difference between really the electrostatic potential at the surface point, and this one is deep inside substrate. So this one is defined as surface potential. Actually, so surface potential is not exactly surface potential, but the surface potential measured from our p-type substrate potential. So please note that in this context, this potential is not exactly potential itself, but the difference between phi at 0 and phi at infinity. So infinity is used for deep substrate in my notation. Okay, so let me just go to this one. So now we understand. In order to understand this problem, we must solve this quite simple but important problem. So left hand side term, Vg minus flap and voltage, that just represent overall bending. So overall potential difference across our entire system, and this right hand term just reveals that, okay, since we have three components, metal, oxide, and semiconductor, and between them we have Vg minus Vfv. However, since we are talking about metal has really negligible voltage drop, so it does not play any role in this voltage division, and only two parts, oxide and semiconductor, they are competing to take this voltage. So simply speaking, the overall potential difference is divided into two parts. What is it? This is the part for silicon or semiconductor, and this is for oxide. So this is a simple division. So 10 is divided by 3 plus 7. It's like this. So now we have to understand what is the form of this surface potential. That is particularly important. Why that is so important? Once we understand the expression for this surface potential, then we can also make a certain reformulation of this oxide field. Then we can make a simple expression for surface potential. So in the modeling of a MOS capacitor, it is critically important. What is the surface potential? How can we express our surface potential using other quantities? Here, what is the other quantity? So usually what we consider is the relation between this silicon charge or substrate charge and surface potential. These are two important quantities, and they have a very well known expression between them. So today we will talk about that relation. How can we express surface potential in terms of our semiconductor charge, or the other way around? So we will talk about this one. But motivation is, since we have to understand this relation, we will spend our entire lecture. Okay. So before talking about the formulas, so I just show you some simulation result. So please make a quantitative or qualitative understanding on this one. So let's just think about this small structure. So here we have silicon, and here we have oxide layer, and work function is just given as a reasonable value, and oxide thickness is 2 nanometer. Okay, so that is nowadays from the viewpoint of our current state-of-the-art device. So this oxide thickness is a little bit thick, but don't care. So yes, and also doping density 10 to the 18. Yes, this is just a reasonable value. So now think about the band diagram. So here this is corresponding to your conduction band, and what is it? This is the maximum of your valence band. Then please estimate the difference between this EC and EB. What is this quantity? The energy difference between EC and EB. This is called as band gap energy. Okay, you know that this is around 1.1 electron volt, and you can understand this is really the case. So I think that actually each tick is placed every 0.5 electron volt. So two ticks is corresponding to 1.0 electron volt. You can easily understand the distance is quite close. This distance is quite close to 2 ticks. So yes, this is silicon's band gap energy. And how about this? Here and there we have a really wide band gap between conduction band of our silicon oxide and valence band of silicon oxide. So it is roughly 9 electron volt. So therefore we have a huge difference between EC and EB. Then please also think about this difference. This difference is roughly 3.1 electron volt, and you can see that, so since our, once again, this is corresponding to 0.5 electron volt, and this 0.5 electron volt is already corresponding to roughly 20 times of your summer energy. Summer energy is corresponding to 0.025 0.025 electron volt. So 20 times of this summer energy is corresponding to just 1 tick in this scale. So it is already quite high energy from our energetic scale. However, you can see that this is corresponding to 3.1 electron volt. So for our usual electron, normal electrons, actually the energy barrier between silicon dioxide and silicon is regarded as infinitely high. Okay, so therefore it is a really small chance to our electrons to overcome this barrier. So it is good to assume that there is no electron at all in this silicon dioxide layer. Okay, and another one is please have a look at the slope. So in the previous lecture, at the end of our class, I told you that the slope of our oxide field and silicon field should be different, the factor of 3, and silicon inside the silicon dioxide we have to have 3 times steeper slope for our electric field. So please have a look at this. Yes, we have a certain slope, so this is corresponding to our oxide field, and please have a look at this slope. Yes, this is corresponding to the surface field calculated from our silicon part, and you know that, yes, as expected, silicon dioxide part has much steeper slope. So this is corresponding to the difference of their permittivity. You know, this one has just 3.9 of vacuum permittivity, and this one is almost 3 times higher than that in the case of silicon. So now this relatively small electric field is relatively small electric field is compensated by this 3 times higher permittivity. So we have to impose the continuity of our displacement vector. Okay. So now you understand many things, and you know that also yes. So today we will talk about something about our band structure, and please try to find out our mid-gap energy or intrinsic level. So maybe you can find somewhere here our intrinsic level, and also you can identify the difference between this level, and here we have a Fermi level of our p-type substrate. So here we have a certain difference, and this energy difference is given as Q times phi b. So please understand this notation. Here phi b just shows that the energetic difference between intrinsic energy level and Fermi level in our p-type substrate. Okay, so this phi b is intentionally taken as a positive number. So please understand, although we have in the case of voltage we have a different sign. Anyway, this phi is regarded as a positive value. Please, then in this case, please try to estimate your phi b value. How large is it? So maybe it is corresponding to approximately 0.5 volt. So in this case, okay, this is the case we will consider from now on, and please have a look at 4 different graphs out of this same system. The only difference is, yes, I just connect the ground 0 voltage to this substrate, so this voltage is just fixed, and instead I change the voltage applied to this gate part. So gate voltage is always changing. We have 4 different gate voltages from the -1 to +1, and let's have a look at. So case 1 is corresponding to far below than 0 volt. So in this case, please think about this one. There is a certain system called as MOS, and one part is grounded, and you just apply quite strong negative voltage, -2 volt, for example. In this case, what we can immediately expect is, okay, well, anyway, there will be certain negative charge induced by this negative voltage, large negative voltage, and there will be certain positive voltage. So in this part, where can you find your metal, and where can you find your oxide in this system? You can find your metal here, and you can find your silicon part here. Yes, so it means that in this highly negatively biased structure, inside your silicon, you will have so many positive charges. Then how can you get such kind of a large number of positive charged particles? The magic is providing a sufficient number of holes. If we have excessive hole inside our silicon substrate, then yes, they are positively charged and they can provide us so positive charge. So think about this one. So now we have a negative charge. So in this silicon part, yes, this is silicon, and we must have positively charged layer, and it was obtained by, please compare it with this part. So here, if I ask you, please try to estimate the overall net charge density, then what will be your answer? Your answer for this deep substrate should be just neutral in this deep substrate. Of course, here we have a lot of holes. How many holes? We will have 10 times 18 per cubic centimeter holes in this system. However, at the same time, we have the same number of 10 to the 18 per cubic centimeter of negatively charged negatively charged acceptors. So they are fully compensate each other. So the net charge density will be 0. However, if we go to this part and change our observation point, then you can see that now our Fermi level, this is corresponding to Fermi level, is even below than our valence band maximum. So simply, usually what we consider is, here we have valence band maximum, and there is our Fermi level. However, in this case, now our Fermi level is located here. What does it mean? We have really high density of whole gas. So we have so many holes, even more than this 10 to the 18 per cubic centimeter. So here we will have a thin layer of excessive holes, and it provides us the required positive charged layer. This is the one. And simply speaking, now let's start from the very basic. In this system, we have metal and oxide, and here we have silicon. However, from the viewpoint of just a newcomer, this silicon is highly doped with a p-type substrate, so we can find tons of holes, and electron is very difficult to find. Yes, finding holes is just natural, and finding an electron, oh, that's really a big deal. So in this case, if we apply negative 2 volt, then according to our current discussion, now we have more holes here concentrated in this surface layer. Then is it something special and surprising or not? Since this is just a p-type layer, a little bit more holes doesn't make any surprise to us. So this one is just called as accumulation. Originally it is p-type region, and in this p-type region we get more holes. So that is the situation in our negatively biased MOS capacitor. Okay, and now let's go to a slightly higher voltage. Then what will happen? So here we have VG, which is given by -0.2 volt, and the band is or EF of our metal should be just 2.0 electron volt. Instead, please think about a case like we have applied -1 + 0 volt to our gate terminal. Then what will be the location of a metal Fermi level? Instead of this 2.0 electron volt, it will be 1.0 electron volt. So in this graph, we will have the lower position of our gate voltage or gate region. So simply speaking, previously it was placed in this upward. However, now it will move to this downward, so gate potential or gate band is moves to downward, so this kind of upskirt will be reduced considerably. So let's go to this way. Please make a comparison. Here now we have the value close to -1 volt, and previously, once again, our formula bell was located here corresponding to 2.0 electron volt, and now when we apply 0.94 electron volt, then now it is corresponding to 0.94 electron volt. So in this left side was increased upward, but that amount of band bending is now reduced to just 0.94. So now you can see that, oh, previously in this part the band was banded upward, but now that was originated from this gate part. Gate part just pick this band upward, but now since that amount is reduced, so now we have of this flat band. So we have already studied the case of a flat band, and in this case we have this completely flat band. The question is, please think about once again the charge density. Here we have still exactly 0 net charge density. Nothing happens. Okay, and how about this? In this case, how many holes are found in this case? Now we can say that the hole density will be exactly 10 to the 18 per cubic centimeter, and it is completely compensated by our acceptor density, like 10 to the 18 per centimeter, per cubic centimeter. So even in this case, even in this surface area, our net charge density will be 0. So it means that if we have to calculate the net charge density inside the entire semiconductor region or silicon region, then the value will be just 0. Simply means that, once again, now we have a certain structure called as MOS, and when we apply here minus 0.94 volt, then if this is just a conventional capacitor, what we expect is, oh, since we have a negative voltage, then maybe we have a negative voltage, negative charges and positive charges in this MOM capacitor. However, please note that this system is not MOM but MOS. They have a different context in both sides, so therefore we have an offset. So even when we apply different voltage, negative voltage, but at this point we have just a neutral situation, and here we have also neutral situation. So we think that, okay, although we have an offset, but this neutral situation is the basis of our discussion. Starting from this neutral voltage, then if we apply additional voltage, then that will introduce positive charge to our gate. And if we apply the voltage even lower than this neutral voltage, then we will have a negative charge in our gate part. So this flat band is the starting point of our whole discussion. Okay, so that is important difference between just normal capacitor and MOS capacitor. So now let's go to the third case, like gate voltage equal to 0. Okay, so if this is just a MOM capacitor, metal and metal, sandwiching our oxide layer, then in this case we will have a neutral condition. But now we understand, since this is a MOS capacitor, actually minus 0.94 volt is the condition for neutrality, and it means that even though we have 0 volt, it is already 0.94 volt positively biased from its neutral condition. So what you can expect is, in this case, okay, if we have a MOS structure, then we will have positively charged particles even though we apply 0 volt, and negatively charged particles in this silicon substrate region. Then how can we apply, or how can we supply this negative charge required for our silicon layer? Of course, in this case, the depletion gives us this kind of negative charge, because acceptor ions are negatively charged. So if it is not compensated by whole gas, then it will give us a negative charge. So please have a look at this band diagram once again. So this is once again the condition for our deep substrate. Yes, in this case we can expect that there are a lot of holes, many holes and almost no electron. And please have a look at the band bending and band diagram shown here. Then what is your expectation about electron density and hole density? Can you expect many electrons since there are sufficiently large energy difference? So electron density would be quite small. And how about hole density? Okay, even in the case of hole density, okay, the energy difference is quite large, so hole will be also quite small. So simply means that in this near the surface or near the interface, we have no electron, no hole. Then what is remaining? Only the negatively charged acceptor ion is left here. That's the reason why our system can show net negative charge. But when we just make some more fine consideration, then this negative charge is solely supported from only our acceptor ions. Okay, so now we will further increase this gate voltage. Then please note that since starting from this -2 electron volt, our gate band bending is always changed toward the negative direction. For example, if we now implement, for example, positive 1.0 electron volt, then our Fermi level for our metal part will be just, sorry about that. Gate voltage is not electron volt. Gate voltage is just 1.0 volt, and our Fermi level will be just -1.0 electron volt. So it means that we can once again bend down in this part. So following this bending down, also our surface area will be affected by this one. Please once again have a look at this one. Now you can immediately understand this part is even more bended than our previous case 3. So the main reason is we have now applied higher gate voltage. So higher gate voltage means that our metal Fermi level should be now -1.0 electron volt. So left part is moved toward downward even severe. So now we have more bending here. In this case, please try once again calculate the net charge density. This is 0 as usual. Then in this part, how many electrons do you expect? So you may expect that there are a lot of electrons. Then how many holes here? Since energy difference is so high, so we have almost no electron at all. So in this bias condition, you can expect that, there are a lot of electrons. So once again, think about your MOS system. Now you apply sufficiently high voltage to your gate, so you expect positive charge collected at your gate part and negative charge collected at your silicon part. Yes, that's true, but this negative charge now originates from not from just depletion layer, but also from another contribution from electron. Once again, this depletion is corresponding to acceptors. This is immobile. They do not move. They are just stay there. Impurities are heavy and inside the silicon lattice, and they do not move in our constellation. However, additional negative charge is supplied from our electron density. So this surface electron is corresponding to this electron density. So think about this one. Once again, we considered p-type substrate. So therefore, finding holes is quite natural. However, you never expect finding electron inside this p-type substrate. But when you apply quite high voltage to your gate, then eventually you find a lot of electrons in your p-type region. So I know that to everybody in this room, that sounds quite natural, but please think, let's come back to our ancestors, and when they just find this phenomena, they was shocked because, you know, this is p-type silicon, so we never expect electron observation, but we can generate a lot of holes. So they shocked and say that, oh, it behaves just like an n-type sample, even though that is a p-type sample, but it behaves like an n-type sample. So they thought that it is as if the type is changes from n-type to, from p-type to n-type. So they thought that this is corresponding to inversion of their doping type. That's the reason why we call this phenomena as inversion. Okay, so inversion means that finding some originally minority carrier in a certain region. So that is called as inversion phenomena in this case. So now we just have quite a short review on the behavior of MOS transistor. I hope that everybody in this room already understand this phenomena, but starting from negative bias, gate bias to positive bias, so what we expect is now changing. And so in my opinion, the very important one, also most important one in these 4 cases to you is this cases. Once again, the existence of this case 3 is the reason why we use MOS. I mean that, think about this case 3. What is it? In this case, although you apply the voltage, but you don't have any electron. Yes, you don't have any electron at all, and there is no mobile carrier. For example, in the case of case 1, you have a lot of holes. Yes, you have many holes. So from the viewpoint of current conduction, this case is much more beneficial than our current case number 3. In this case, in case 3, we intentionally applied a certain gate voltage to eliminate all holes, and our surface region here, shown here, now disable to conduct current. So its conductivity is quite low. In other words, its resistivity goes very high. However, the existence of this, insulator-like behavior provide us very important implication. So I mean that, now let's go to this one. We have a certain voltage range. for a certain voltage range. In this voltage range, we have a certain range where the device cannot conduct the current, and beyond a certain gate voltage, now we have electrons and it can conduct. So now it can conduct current. However, there exists certain voltage region. It means that we can now turn off our transistor, our device. That is important actually. Current conduction is well done by just a conductor. If we use a conductor, then we can always allow current conduction. The key point of our electronic device is not actually conduction, but the ability to turn off our device and not allow to conduct current. So this MOS structure allows us that probability. By applying relatively low gate bias, we can control the number of charge carriers, and it is corresponding to the very important point of our MOS capacitor. Okay, I hope that is just one more repeating the knowledge you know already. So okay, that was just quite conventional review on our MOS transistor, and I expect that you have already seen it before in your previous courses. But today's lecture is more devoted to the derivation of a general relation. So let's go to this way. Before going to the this derivation, so let me explain a little bit more about our TCAD simulation result. One is the threshold voltage. So in this figure, I just draw certain quantities as functions of the gate voltage. Yes, it is just a collection of our previous 4 cases. So please think about this one. Yes, there was one case here, case 1, and there was another voltage corresponding to case 2, and what was the case 3? Yes, here we have a case 3 and case 4. We had these 4 representative behavior, and you know that this condition is corresponding to flat band. In this flat band case, how many charges are available to us? Actually, net charge density is identically 0 at flat band condition. So this blue or red, any kind of this one is corresponding to overall charge Q sub S, and you can see a dip in this graph. So actually, why we have stopped here is only because we have a finite points in here. If we can make even further resolution nearby this flat band, then of course this value will go down exactly 0. So please note that this is just an artifact for our graphical representation. We have the real dip. So here we have positive charges in its QS sign, and here we have QS sign equal to negative. Simply means that beyond this flat band voltage, then your silicon region has a net negative charge. Of course, how can we get these negative charges? First, it was provided from acceptors due to depletion. After that, it is provided from also inversion electrons. That is shown here. Please have a look at this one. This blue curve is corresponding to depletion charge. So contribution of our acceptors. And this green one is corresponding to our inversion charge. So that is corresponding to electrons. So when you have a look at, for example, about 0.3 volt, it has really small number, and if we go to 0.4, it has a higher number. 0.5, we have an even higher number. However, anyway, in this case, the number of electrons or contributions of electron is far below from our depletion layer. So in this case, we can completely neglect the electronic contribution. However, please have a look at this point. What is it? This is the point where contribution of depletion and inversion electron become comparable, and beyond this point, actually almost all of additional charge is supplied from just inversion electron. Okay, so simply speaking, if I make a certain analogy, so this depletion charge start first, and inversion charge does not start, just wait. However, once it starts, then it shows much steeper increase than this moderate change of our depletion charge. Soon after, it just catch up the depletion charge, and beyond this point, all of charges are supplied by our electrons. So that is the internal understanding on situation in silicon. So we have two different guys. One guy is always working hard, however, actually he has low potential. And we have another guy which is quite lazy, but once it starts, then outperform the first one. So this guy is corresponding to electron. Okay, so same graph can be drawn in different scale. So in this page, I just show you semi-logarithmic scale. X-axis is corresponding to gate voltage, and y-axis is corresponding to charges. However, I just took the logarithmic scale. And please go to this way. If we draw the same quantity with linear scale, then it becomes more clearer. Beyond this flat band voltage, first we have moderate increase of our depletion charge. However, contribution of depletion charge is just stagnated, and there is a certain maximum value of our maximum charge from the depletion layer. Instead, please have a look at this green line. This green line is a contribution from our inversion charge, so electrons, and beyond a certain level, roughly speaking, for example, beyond this level, beyond this voltage, how many electrons are there? Then actually it is quite negligible. Of course, if we ask the exact value, we can say, please have a look at this value. For example, 0.3 volt case, maybe we have 10 to the 10 per square centimeter. However, in this linear scale, if we go to 0.3 here, then how many electrons are there? Yes, it is about 10 to the 10 per square centimeter, but here we have 10 to the 13 as a linear scale. So 10 to the 10 is just 1/1000th of this 10 to the 13. So it is not recognized as a meaningful number. So nothing, no electron at all. However, beyond this point, usually called as threshold voltage, then now this contribution, electronic contribution, just dominate the overall charge state. Okay, overall charge, almost all of negative charge additionally supplied comes from the inversion charges. Okay, once again, yes. So before starting our main story, the derivation of this relation between Qs and surface potential, we first introduce a simple approximation following the depletion approximation. Once after we understand this depletion approximation, then we will switch it to the rigorous derivation. Okay, I think that is better than following textbook's presentation. Okay, now think about this one. We will use depletion approximation and neglect electronic contribution. How can we neglect electronic contribution? It means that we do not consider the case like this. This part, by using just depletion approximation, we cannot consider this part. Then what is the operation point of our interest right now? We are more or less interested with this part. Then how can we consider this part later? So it will be done in different way, and anyway, for a while, just believe me. So here we can sufficiently say that electron is quite small. We have a small number of electrons, so we do not consider contribution from electrons. Then neglect electrons. Then what we can do is just to calculate the holes, but hole is treated with the depletion approximation, so hole is completely depleted up to the depletion layer. After that, beyond this point, then it is completely also recovered. So simply speaking, if we consider a certain depletion width, then beyond this point, our net charge density is once again 0, and in this part we have fully negative charge corresponding to minus Q times Na. This is not the net charge inside our depletion layer. Okay, so if we have this depletion layer, then let's say that this is depletion with WD, then this is electric field, and by integrating this electric field, we can get the potential difference between these 2 points. The area of this triangle is corresponding to just surface potential. Why? Because we define surface potential as a potential difference between surface point and deep substrate, and this area is corresponding to this surface potential. So please have a look at this one. The area of a triangle is corresponding to surface potential. Please note that this is electric field versus position. So by integrating once, we will get the potential difference. And how can you get this area? Since this is just a normal triangle, we can multiply this one side and the other side. So one side is corresponding to WD, and this another side, normal side, is corresponding to this one, because we know this is the slope of our electric field. So now we can apply this one with tangential, so we can have this one. So please check it. Once again, what I wanted to say is, in this graph, in this field versus position graphs, so this slope is corresponding to minus Q Na divided by silicon permittivity. If you know the Poisson equation, then you can easily understand this is the truth. Why it is truth? Actually, we have to consider electron contribution and hole contribution, but in this depletion approximation, we intentionally eliminate both of holes and electrons, so we can consider only negatively charged acceptors in this case. So that's the reason why this slope is given by this number, and this is corresponding to tangent. So this is one side. So the length of this triangle or this side can be simply written as Q Na epsilon silicon times WD as written here. So from this simple calculation, now we can say that the depletion width of our depletion layer is proportional to the square root of surface potential. If surface potential is increased, then we will have wider and wider depletion width, and since depletion width is becoming even wider, so we will have more and more depletion charge. Depletion charge is simply given by minus QNA. This is volume density of our depletion, volume charge density of our depletion layer, and thickness of that one. So we will have this simple relation. So it looks perfect. However, please understand there is some limitations. What is the limitation? First of all, we have neglected electronic contribution, so it should be applied below threshold voltage. Okay, if we cannot apply this approximation beyond the threshold voltage, and also we have implemented the depletion approximation, so we have to understand small errors originated from depletion approximation itself. But you know, more or less that gives us overall trend quite well. So you can see that the simple relation this one. In this case, our QD is actually corresponding to QS, because of course QS, our net charge density, can be decomposed into two parts. What? One is depletion charge and another one is inversion charge. However, right now we are considering the gate voltage far lower than threshold voltage, so this does not have any contribution. So depletion charge can be regarded as just all over our substrate charge, silicon charge, semiconductor charge, whatever. Okay, so now you can see that this relation. Oh, charge collected in our substrate is just proportional to what? Proportional to square root of surface potential. That's the point. That is really important point. For example, let's say that you had previously bending like just 0.1 volt, surface potential is 0.1 volt. Now you go to 0.4 volt, then how many charges will be induced by this depletion approximation? So you will have just 2 times more depletion charges when surface potential changed from 0.1 to 0.4. 4 times larger surface bending is corresponding to just 2 times larger amount of depletion charges. So I would say that this is quite moderate, not exponential. It is just to say that if you increase surface bending 10 times, then it means that you just have 3 times larger charges. Let me just have a look at this curve. So up to now we are talking about the condition below threshold voltage. Yes, here we have somewhere here threshold voltage, and we are talking about this blue curve. So please have a look at this blue curve. How do you feel? So here we have certain blue curve corresponding to Q sub D, and its behavior is just moderate, just like a smooth curve, not that much drastically exploding. Okay, so this is depletion approximation. So okay, this is revealing the same one, but please just let me do it following the our textbook. Okay, this is a potential profile obtained from our depletion approximation. Here we have a certain potential. Yes. Here, why do we have this negative value? The reason why we have a negative value is this is a p-type layer. In order to have many holes, actually we must have negative potential here. And if we go to this way, beyond our depletion layer, then net charge density is assumed to be just 0. So everything is just quite homogeneous. And once we enter into this depletion layer, now we see a constant increase, linear increase of our electric field, and potential is obtained from one-time integration of electric field. So a constant linear function is integrated, therefore we will have a parabolic behavior. So you can see that this parabolic behavior is originated from just linear behavior of our electric field shown here. And also why we have a linear variation of electric field in this point, this is because we have a constant space charge region in this depletion layer. Okay, so now we have this form. Then let's consider a very special case, very special case. Now if I ask you how many holes are there, then your answer should be, okay, at this point hole density is given by Ni times, yes, this phi b divided by kBt over q. That will be your answer. So yes, this is the hole density. Then please also answer my question. If this position we have a minus, if this potential is given as phi b, then how many electrons are there? Then you must say, in this case, electron density is also Ni times exponential phi b divided by kBt over q. So are you all with me? So simply speaking, what I did is, position wise we have a different potential. So we just use electron density is Ni times exponential potential divided by thermal voltage, and also I just applied the fact that hole density is given by Ni times exponential minus potential divided by thermal voltage. So yes, this is the case. Are you with me? Then important one is, yes, this value and this value happen to be the same. So in this case, if you are just an observer, then you can see that, okay, previously I implemented the acceptors like 10 to the 18 per cubic centimeter. So I expect 10 to the 18 per cubic centimeter hole density. However, in this special case, I can see also a carrier density of 10 to the 18 per cubic centimeter, but it is not from holes, it is from electrons. Electrons has the same density of our original doping density, acceptor density. So it means that we expected the same amount of holes, but we can find the same amount of electron. Wow, it's just like a magic. So here we have electron. Here we have holes. Yep. So this is electron. Just like a magic, we just change the polarity of carriers. So this condition is special, and it is regarded as an indicator for inversion property. Okay, where do we have inversion? This is theoretically, this is the starting point, or the point where we have inversion. Okay, now we have comparable number of electrons to our bulk hole density. So this is inversion. So are you with me? In order to get this condition, actually our surface potential, so please note that our surface potential is defined as a difference between our bulk potential and surface potential, and this difference should be actually 2 times phi b. Why we have 2 times phi b? 1 phi b, if we have a surface potential corresponding to 1 phi b, then we will have this form. And if we have another phi b, then now we can increase our potential up to this point, then we can have inversion of electrostatic potential. Okay, so this is theoretically, this is the condition for inversion phenomenon. So but in reality, as an engineer, so it is really difficult to measure this point. Why? Can you see electron gas actually? Or can you, if you can see using certain means, then can you measure the density of electron gas? So it is quite difficult to visualize or measure. So actually this is corresponding to a certain theoretical quantity, and in reality we just say that if we have considerable amount of current conduction, then that is an indication of a sufficient number of electrons. So that is regarded as the starting point of inversion layer. Okay, so up to now I explained this point, and we are in hurry, and now up to now we have well used this depletion approximation. So looks quite okay. However, when we have surface potential quite close to 2 times phi b, you know, this phi b is sometimes around 0.4 or 0.5 electron just volt. Yes, this is quite a large quantity. So 2 times means that we are now talking about surface bending corresponding to 0.8 or 1.0 volt. When we have such kind of a huge potential bending, then we should ask ourselves the justification of our depletion layer. The reason why we use depletion layer, depletion approximation, was there is no electron contribution. The electron density can be negligible. However, when we have this condition, now we have the same amount of electron at the surface layer. Oh, so we cannot neglect it any longer. Then the natural question is, then what will happen if we go to even higher gate voltage? Then what will happen to our depletion charge density? If we apply even higher gate voltage, so let me just my long discussion. If we apply even higher voltage, gate voltage, then the surface potential will be increased, and it will give us even more depletion charge density. However, this is a long discussion. So, you know, as shown, as written in my last sentence here, beyond this level, so threshold voltage, now surface potential is almost approximately pinned. I mean that even though you have applied, for example, 1 volt additionally, then what you can think is, oh, since now we have additional 1 volt, at least a half volt is affected by this, will affect this surface potential bending, but it's not the case. Of course, this surface potential can increase a little bit, however, compared with the change of our gate voltage. Now, beyond this level, the amount of surface potential change becomes really minimized. So that is some point we have to understand. So let me explain a little bit more. Maybe I have something here. Okay. So if we understand this one, then surface potential is pinned and it does not grow any further, then we can see that this graph is not an analytical result, but it is obtained from simulation result. And you know that here, beyond this point, actually depletion charge does not grow at all. So it is almost constant in this semi-logarithmic scale. Well, if you don't like a semi-logarithmic scale, then let's come back to our linear scale. This is a really linear scale graph. Then what happens? So can you recognize? I think that maybe something is wrong in our system. Okay, so it was just stopped. So please, this one. This is really linear graph, and even in this case, you can see that, wow, the depletion charge is almost fixed. What does it mean? It means that although, so please think about this one. This point is corresponding to gate voltage of 1 volt, and this point is corresponding to gate voltage of 2 volt. It means that starting from this point, we applied additionally 1 volt, and you know that this additional 1 volt should be divided into oxide layer and silicon layer, but this almost flat curve strongly suggests that actually in this case silicon does not take any further surface potential. Surface potential is just fixed to a certain value, and additional voltage is all consumed by what? Consumed by our oxide layer. Oxide layer takes all of additionally applied potential, and surface potential is just fixed to almost constant value. So why I'm saying that almost? Because it is increasing. However, its increment is much smaller than the change of gate voltage. Okay, so if we change 1 volt and it just change a few millivolt, then virtually it does not grow at all. Okay, I'm so sorry about this slow lecture progress, but it is so important. I think that this is at the heart of our entire class, so we must spend sufficient time on this one. So now let's wrap up today's lecture, and I will continue our discussion in next one. Then please have a look at our lecture contents. And although today I do not ask you to do the homework, but I recommend you to, eventually you will have to do homework number 4. So please prepare this homework in advance. Thank you and bye.